Dear Professor, the topic we're going to talk about is the backtracking algorithm. As for the questions that cannot solve in polynomial time, we can use the exhaustive method to find a solution. That is the brute force algorithm, since that in some cases we have no option but to use brute force, even if it has a very bad time complexity. However, in most cases, backtracking is a much better choice. The core idea of the backtracking algorithm is that it will solve problems recursively by trying to build a solution incrementally. That is, one component of a solution at a time. And we will remove those solutions that fail to satisfy the constraints of the problem at any point of time. And that is the most important factor for the efficiency of this algorithm, is that if the solution has broken the constraints, we do not need to go any further and just do a backtrack. Then, as for a specific problem, how to build a backtrack algorithm? First, we need to generate a state space tree to show the current solution states and the current problem states. Second, we need to construct the end condition. That is, if each possible solution enters the end condition, this solution will be added to the final answer. Third, we need to make a choice to choose which state to go to further recursion. Fourth, if the solution violated the constraints, it will be discarded. Next, we are going to talk about one classical application of the backtracking algorithm, n-queen problem. What is an n-queen problem? Suppose that we put n queens on an n by n grid chess set so that they cannot attack each other. That is, any two queens cannot be on the same row, the same column, or the same diagonal line. And the question is that how many possible solutions are there? For the convenience of the visualization, we will give an example which n equals 4. To put our first queen, we will put it on the first row. And it has 4 choices, here, 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 and here. Suppose we choose our first queen is put here and go further. The second queen is put on the second row. It has 4 choices, 2, here, 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 and here. If we put our second queen here, it violates the constraints. If we put our second queen here, it also violates the constraints. Here, it does not violate the constraints. Here, it's the same. So we have 2 choices, here and here. For these 2 choices, we will go further, and we choose this choice as our current partially solution. We will put the third queen on the third row. It also has 4 choices, here, 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 and here. However, if we put our third queen here, here, and here, it violates the constraints. So we have no choice but to put our third queen here. And that's the only choice. Next, we will go to put our first queen. It is easy to see that our first queen also has only one choice. That is, it can only be put here. And this total procedure gives us our one solution. The first queen is put here, the second queen is put here, the third queen is put here, and the fourth queen is put here. And that enters our end position, or end condition. That is, we need to put 4 queens on our chess set, and this solution will be added to the final answer. The following is a procedure code for our algorithm. For the column in range from 0 to queen num -1, we will do a check for each grid, which is specified by the row and the column. That is, if the column we will use this check function to determine whether the partially solution has violated the constraints. If not, it will return true. If it returns true, we will record the current solution state. And if the current solution has entered the end condition, that is, we have go to the left row, that means this is a correct solution, and we will add it to the final answer. If not, we will go further for further recursion. That is all. Thank you.